Okay, I want to explain this question a little bit more. So we've actually got three objects involved here. We've got Team A, the rope, and Team B. So I'm going to draw three body diagrams for Team A, Team B, and the rope. So we've got Team A over here, we've got the rope, and we've got Team B. Okay, so this is Team A, this is Team B, and then this is the rope in the middle. So what's happening is Team B has got a tension force this way and a friction force this way, okay, with the ground. Team A has got a tension force this way, the rope is pulling Team A, and a friction force this way. The rope has got a tension in this direction and a tension in this direction. So the Newton's third law, the pairs here, are there's a pair of forces, okay, and there's a pair of forces. Those are the Newton's third law pairs. So the three body diagrams, as I've just of the rope, is a little bit confusing. It is just a tension in opposite directions. One tension towards Team B and one tension towards Team A. Now, at the beginning, these are equal, right? At the start, the rope does not move. How does Team B win? Well, what Team B does, Team B pushes the ground, to the left. Team B pushes the ground to the left from Newton's third law. The ground pushes Team B to the right. So now what's happened, if we look at Team B has increased their friction. Their friction has increased, but the tension is still the same. Okay. Well, actually, no, that's not quite true. The tension will get a little bit bigger because the rope also, here's my rope, the rope has now got to move to the right. So the rope has got to have a slightly bigger tension in that direction than it does in this direction, because the rope has got to move to the right. Okay, so now we can say from Newton's second law, there is a resultant force to the right. So Team B moves to the right. So actually, remember, these are Newton's third law pairs. These are a Newton's third law pair. So actually, these have always got the same magnitude. So actually, if the tension increases, this tension must increase as well. But the resultant force is definitely to the right because they've got to move that way. So the rope and the rope moves to the right. Now we've also got to think about Team A. Team A must also move to the right. So the tension force here must also increase because their frictional force remains a little bit smaller. They will move to the right. So from Newton's second law, there's a resultant force to the right, so Team B moves to the right, and the rope moves to the right, and Team A moves to the right. So you've actually remember that in Newton's third law, these ones that I've circled are always equal in magnitude and opposite in direction. So the overall idea is these ones, if we look at it as one big object now, that force and that force have got the same magnitude, that force and that force have got the same magnitude. So if we just look at it as one big object, all those tensions are all the same, so they just kind of cancel. We basically have got two frictions. We've got a friction here, which must be bigger than the friction here. So as one object, the friction on team B is greater than the friction in team A, so they move to the right, so they have a resultant force to the right to accelerate to the right. So we it's a lot more complicated than what the mark scheme says and what my answer here says, because you've actually got these three objects: team B, team A, and the rope. So you have to try and explain an answer to that. Okay, there we go.